So thank you, Stuart, for this. I could see in the website of Strathclyde University that you're the Undergraduate Course Director for the department.
Yeah.
Can you explain what's the purpose of that?
So my role in the Mechanical and Aerospace Engineering department is Undergraduate Course Director. So I look after all of our undergraduate courses across mechanical and aeromechanical, and so across all 5 years here in Scotland. So about 1,000 students, and I look after their curriculum. I look after them, their general experience, make sure they have a good time, and make sure they're learning the things they need to learn in order to be successful engineers.
So is it something related to the institution, or is something you do with students themselves?
It's kind of both. It's a defined role in the institution, and I'm ultimately responsible for the undergraduate students. I have an excellent team of people who help me with individual years and individual modules, but I'm there when the day-to-day running runs itself. It's my job to look after the weird occurrences when things go slightly strange or wrong, and try and fix them, and then also look a bit further forward about what we're teaching our students and how to make them useful engineers in the coming 20, 30 years. Because when they graduate, they've got the whole career in front of them. So you're trying to look ahead as far enough to make them useful.
How is this role related to, let's say, the goals, the program of the university in terms of other people doing this stuff?
Yeah. So the University of Strathclyde has a very clear definition. It's a place of useful learning. So that kind of underpins everything we want to do, and I just take that on board. My job is to make sure that everything the students do is for a reason. It's not just because we've always done it. It's not because one person thinks it's the right idea. It's because, what's the most useful thing for these people to learn? And every department has their own slight take on that. What's useful for a mechanical aerospace engineer is different from a civil engineer or a historian, whatever it may be. But you kind of take it as a whole. Strathclyde has a lot of links with industry, and which we'll probably touch on a bit later on as well. And it's very important to take on board what industry is saying, of what they need from their graduates when they graduate, each year. But also take that with a grain of salt sometimes, because inevitably they're looking more at the short-term needs, which is that's their job, right? Because we've got to look at, we might be told we need lots more of X, but Y is where the industry is going to go to in the next 10, 15 years. We need to start giving our students the tools to be able to learn these new technologies. And one important thing that I try to get across to the students is that we're not teaching them specific skills, in that they're not going to spend their days doing equations from thermodynamics, right? We teach them how to learn new skills as they evolve, because we can't possibly know what's going to happen. So there's a lot of emphasis moving towards the computational side, programming, data analysis, giving the fundamentals so they can understand in whatever job they do how to succeed.
And can you maybe explain a bit more about, you said about the challenge of talking with the industry, trying to integrate what they want, but also at the same time trying to not get fixed on a local minimum.
Yeah, exactly. Exactly. So
how do you do that?
Yeah, so it's reading between the lines. If you're people will often tell you their proposed solution rather than actually explain what the problem is, if that makes sense. So the industry will say, we need this, we need that, we need this, when in fact you want to drill down, and this applies across the board, to what's a fundamental problem, what tasks will these students have to tackle, what's the actual problem they're facing, and then come up from the ground up, what is our solution to it, rather than someone saying you should teach this one specific thing. Because frequently it'll be, you should learn this tool, or you should learn this specific topic, whereas you can take a step back and go, that's a problem, but how can we build the structures to let them learn any of those things?
So like the what the industry is saying is the solution can be seen as a symptom of what we have to understand throughout the...
Exactly. But you've got to dig a bit deeper, because there will be some underlying problem they want our students to solve, and that's what we've got. That's our job, because we're not teaching them specific things. It's the general tools to let them learn all this stuff.
Okay. And I also seen the student voice on your website.
Yeah.
What's that?
So this is the downside of, so we'll get into my background, I'm sure, further on, but I'm quite a computational guy. Okay. And in my teaching, which has kind of evolved over the years, as an engineer, I want feedback, I want data to see how good am I at teaching. That's where it all started. This is a common requirement across educational professionals, and there are certain tools that will let us survey the students. So traditionally, a student survey for a class might be a bit of paper saying, how did you like the lecture, how did you like the room, and any other comments. Right? You give out all the paper, get it all back. And some people did that, but there's a lot of effort. I wanted better data over longer periods of time, more consistent data. So I built a system that's basically online. You send the students a link, they look at their mobile phones, they quickly answer the questions, and then you can collect that feedback from every single class in the Faculty of Engineering at Strathclyde.
And are you doing that only for the classes you're teaching?
No, but that's it. So
that's part of the...
Yeah. So the system runs across every single class because in education, some members of staff were doing these surveys on the paper anyway. Mm-hmm. And they're the ones you don't have to worry about because they've seen, like, I want to improve my teaching. Let's try and change it. The people who don't think they have to improve their teaching or don't even think about it, they're the ones you also want to survey, but you don't want to make them do anything because they've got enough things going on. So you make it all happen automatically. It just happens. The students fill it in, results come in, and a key aspect of student voice is when all the results come in, the lecturers write a response to those comments. And because it's online, it can be done quite quickly. We have a survey open for a week. The next week, the lecturers write a response and say, yep, I agree with that comment, or more often, this is why we do that this way.
Right.
It's not a tool just to change at the whim of a student, but a lot of it is communication. So it's just explaining why you're doing something. Right. They're like, why don't you give those answers until week 8? Why don't you do this thing? There's not really a reason, but it might not be vocalized. So it's a good way to clarify that to students.
Okay. And is it a process going on all the year, during the year, or?
Yeah, so it happens the middle and the end of each semester.
Oh, okay.
So we try and do it in the middle of the semester to make the students feel like they're actually getting listened to, make change. If there's something wrong in the class as it's going, you can fix it, great. And then at the end to try and capture assessment exams, things like that. So it happens once or twice every semester.
Okay, nice. And do you teach also some courses?
Yeah, so I teach one very big class. So I teach Engineering Mechanics 1, so it's our first year class. And that's
undergraduate, right?
Yeah, and that's to 330 students from mechanical, electrical, mechanical, naval architects, and the product design engineers as well. Okay. So it's a very big class. It's the biggest in the faculty, and it fills 2 roles. It's a classical mechanics class with physics of how things move, but the primary role is trying to undo some of the teaching done at high school. In our education system, we, especially at sort of highers in Scotland and A-levels, it's about learning the equations, learning the test, learning the exam, and just memorizing these things and being able to. There's not the understanding. Whereas in engineering, as I said before, it's not about learning the specific equation because you look that up. Okay. It's about the understanding the concepts. So we spend a long time drilling right back to a conceptual understanding of how the world works, how the world moves, and lots of fun demonstrations and things. And there's some interesting points around we live in the world. We live in a physical world. We all obey the laws of physics. So you'd assume we'd have a good assumption of how these laws work, but some of them are very counterintuitive. So the conceptual stuff is quite important because you've got to understand what's going on a conceptual level because your eyes can deceive you. So in the example of sort of reference frames and rotating reference frames, which carries on to the space stuff, you can be experiencing something very different than what the actual overall system is. Your perception can be very different. So it's a lot of fun to do. And very rewarding. It takes a lot of my time on teaching. So.
Yeah. How much?
So we teach 4 hours a week. So it's.
Okay. And how much time do you spend not teaching but working on teaching?
All the rest of the time, basically. So the majority of my time is spent on sort of the management of all the courses. But when you are developing a course, initially you have to put a lot of hours in, like 10, 20 hours of preparation to teach 1 hour.
Okay.
Is a general rule, and that's pretty standard. But then you also, as you go, you want to keep on improving, and I teach with a colleague, and we're bouncing ideas and constantly improving these things. So you work on it as you go, and there's also the marking of the coursework and the exams as well, which is, so in a big class that's a big downside.
Okay, and then the question becomes, how can you put together outreach, teaching, research?
Yeah.
Yes.
Well, this is
personal life.
Yeah, but yeah, it's a balance. You've got to learn to say no to things. If it's something you really want to do, you do it. If it's something you're not really interested in, you should learn to say no. That's a general rule, I think, in life. So different times of the year, my teaching, the 2 semesters are basically 2 11-week blocks in the year where it's very intense teaching, but out from like that, I'm doing a bit of marking, but then we get a bit more freedom. Research bubbles along all the time. Second supervising a few PhDs, have meetings with them, seeing what's going on, trying to do some of my own work. The outreach comes, again, at fairly random times, but the outreach we do in the department is fairly planned. We're doing it for a number of years, so you know when that's coming, you can prepare and improve. And it's a lot like the teaching, really, in that you put a lot of effort into the initial developing the materials, then you're just iterating on that, constantly keeping up to date, improving it, things like that. Okay. But it's a balancing act, and anyone working in academia or any research job anywhere in industry will tell you it's always a balancing act. Never quite enough time.
And do you think the best way to do it is to say no, to learn to say no?
Yeah. But it is hard, especially if you want to say yes.
Yeah.
Especially it's easy to say no to some rubbish job. Like, okay, do you want to do some extra marking? Like, no. But it's like, do you want to do this outreach thing in this cool place? And you just might not have time, and it's hard. It's hard to say no, but you've got to do it because you've got to give yourself that space. And especially if there's any research involved in your job, you have to give it. It can't just be spent 40 hours working on that paper, on that problem. There's also got to be the slack built in to have some thoughts, to actually think about something new and novel. Right. And you can't do that when you're head down all the time. So the hardest thing is saying no to something and then not immediately filling that gap. Because you're not just saying no because, my calendar's full. Right. It's like you have to protect time to do thinking stuff, which is go for a walk, go for a run, whatever it may be. And that's the trick, because you feel very guilty, but that long term, that's how you can keep sane and also produce good research work, because you've got to give yourself space to think. Okay, that's nice to hear for me, because I don't know, maybe it's a personal comment, but I felt like as scientists, we're triggered to think about limitlessness. Yeah. and so we think about ourselves to be limitless. Yeah. As you get older, it's interesting actually. So as you get older, you discover more and more of your limits. But then you also discover that a lot of those limits are self-imposed. And so I've got a young family, and you realise previous limits would be, I can't possibly operate on a bad night's sleep. If I sleep 2 hours a night, 3 hours a night, I'm going to be incapable of doing my job. Right. When you have a baby, you realise you can, you actually can do it because you're forced to do it. It's a forcing function. So you discover a lot of these limits are self-imposed. So you then the realisation is you have much more control over what you do. You do everything with intention, and then set your own limits, and that's both in a how much can I do, but also in how little can I do of that thing. And as long as it's intentional and you reappraise it, it's fine. Right. That'd be my nice to know. Yeah, you can't do everything, is my point. And it becomes less and less possible to do everything. Right.
And maybe it's still on that. How do you decide what's the best to do? Like, do you have a pie chart in advance and you say, okay, my 60% of my time is this?
Yeah, I wish it was that organised. No, not really. It's a really good question. How do you decide what to do? As you progress in your career, it becomes less and less about your direct output and more about helping other people with their output. And that's a very different problem, a very different ways to spend time. In that, if I'm managing a team of PhD students who are helping to mark some of my work there, so one of my classes. Like, I could just go, right, I'll do it all myself and spend 25 hours straight marking, but that's not a good use of my time. So the best use of my time is to spend 4 hours with those students, going through them, saying what I would do, how I would do it, things like that. And you become, as you progress in any career, I think, especially in research and academia, you've got to think of yourself as a multiplier rather than an additive. Okay. So you can throw hours at something. You can say, right, I'm going to set aside that day, I'm going to help in that. But the best thing to do is just help everyone improve so they're more efficient with their hours, they can do more things, they can take on other tasks. And it's that kind of balance. Okay. And that's a hard one. And there's no pie chart, it's done on you try and think long term. And also I'm a software guy at heart, systems, processes, automation. There's a lot of things people do just because they've always done it, and there may be more efficient ways of doing that in a more rigorous way. Right. So always kind of push those. If you're going to do anything twice, automate it. Because inevitably it won't be twice, but 3, 4, 5 times, and it saves you time. So investment in automation would be another bit of advice. There's lots of great tools for that, whichever. Yeah, if we bash scripts, it can be programs wherever it may be.
Right. Can you maybe talk a bit about your background and what's your research about?
Yeah, so my academic background, I did my undergraduate degree at Sheffield in aerospace engineering, the MEng, and after that, was actually quite sick of it. I chose aerospace engineering because I had no idea what I wanted to do. And at Sheffield anyway, aerospace engineering was a new course, and it was basically the first 2 years worth of content from sort of mechanical, electrical, computational control, those things. So I thought, okay, learn everything. So it's great. I love the course, but by the end of it, I was like a bit burnt out by it. So I actually spent 18 months working in Canada in a shop, which is great, in Vancouver, just living a nice life. And then, but all good things must come to an end. And I learned a lot of lessons. I was ended up managing a clothes shop. I learned a lot of things at the time I didn't realise helped me a lot in my career. But came back to the UK and started working in engineering consultancy for a company here in Glasgow. Okay. Working on nuclear and defence contracts, which sounds much more exciting than it is. If anyone who works in nuclear and defence industries will tell you it's not as sexy as it sounds. But worked on a few projects in nuclear decommissioning up in Dounreay in Caithness, very north of Scotland. There's an old, it was a nuclear reactor that was the UK used to make as plutonium. Mm-hmm. So a very messy business. The cleanup process will take decades, double-digit decades probably. Then I worked on some of the UK's nuclear submarines being developed. But I was still relatively young at that point. Worked there for 2.5 years, different contracts, but it wasn't really... Nuclear in particular, but also defence, moves very, very slowly. For good reason. Like, you're not going to knock up a design for a nuclear reactor or clean one up in like 6 weeks. Like, these things move very slowly, but as a young guy, I was like, it's boring. So I then started looking elsewhere, and I saw that there were PhD opportunities in sort of the space field, orbit mechanics and autonomy, which I'm very interested in. I'd done a little bit of that in my undergraduate, but not much. But I thought, why not? Go for it. So I applied for a few PhDs and got offered one in Glasgow, which is nice. And then just started on that road. So then spent the next 3 and a bit years on my PhD work, which was autonomous systems in space. It was a general topic. There's a few different aspects to it. It was co-funded by ESA. So I was working on a few different ESA projects that were very cool, have since been cancelled, which I think is the way for most of these things. But ended up kind of focusing on formation flying and building the technologies or the fundamentals, building blocks of autonomous systems to manage that. So you can do formation flying far outside the real-time communication reach of Earth. So in my particular use case was for a formation of space telescopes at the second Earth-Moon Lagrange point, which would have been able technically to directly image an exoplanet. Right. So there's occlusion. Not to get too tell me if there's too much detail.
No, let's go into detail.
You have...
I did something about that as well.
Yeah, so you're looking... So for the watchers and listeners, you have a...
Maybe we should also explain what's Lagrange point.
Yeah, well, depends how long I can go into full lecture mode at that point. So, first of all, you can have a space telescope, and you can look for the wobbles in a star to see where an exoplanet is, and then you can work out actually a surprising amount from that wobble. But the light of the star is so much brighter than the planet. Even those planets that we're generally looking at are very big. You can't directly get the light from the planets, or with some few tricks you can try, but it's very difficult. So one solution to this is to have multiple telescopes, all looking at the star, and you use a feature of waves and light in that you can have constructive or destructive interference. So you have most of the telescopes aligned in one way, and then have one telescope aligned half a wavelength off. So then you can cancel the light from the star, and still left with the light from the planet.
Right. Now,
this involves positioning these spacecraft in space to the accuracy of half a wavelength of light. So it's exceptionally difficult to do. But there's work going on. There's sort of it's interferometry is the area of physics that's involved with, and it is used. And the LISA mission was a prototype of laser interferometry, so formation flying exceptionally tight tolerances. But if you can do that, you could see the planet. You could see the planet around the other star. You could see what color it is, but you could also see the light shine through its atmosphere. You could get chemical compositions. You could do everything you could.
So you will get all the spectrum.
Yeah. You could see other organics in the atmosphere. Like, it'd be a game changer.
Right.
Problem, technically very difficult and also very expensive, but very cool. So that was a lot of my work, and my work was on how to maintain those formations, or how to start trying to. It's a very, very difficult job. And the reason you need autonomy is the best place for these telescopes. One of the good places for these telescopes are the Lagrange points. So these are balance points in the gravitational field of the solar system, where if you've got rotating bodies in the rotating frame, there's a certain point where you can think about if the force throwing you out is balanced by the force of gravity pulling in, so you basically can stay roughly in a sort of saddle point. And this is useful. You're rotating around with the moon, or if it's Earth Moon, or with the Earth if it's Sun Earth. And any two bodies have these points, and you rotate with them. And it means you have your back always to the sun. So you just have the solar panels on your back, and you're always facing away from the sun. So you've got a nice consistent power source, and you also have no interference from the light from the sun, because obviously the optics are very, very sensitive. So that's where it's a common place to put big space telescopes. The problem is it's not a perfect balance point, and the dynamics are quite funky. You get some orbits called halo orbits. So you can't orbit. I'm doing for the audio listeners. You can't orbit these points, but it's basically you sort of wobble around them in a semi-consistent manner, and then you maintain a formation within that. So it's interesting orbital mechanics stuff.
Okay. And the idea is to go on the Earth-Moon Lagrange point, to get rid of the noise coming from Earth.
So for the telescopes, it's normally Sun-Earth, I think, just because the light is more of a problem. But also, you can be on Earth-Moon, and your back's always to the other bodies. You're sort of the furthest one out. Mm-hmm. So the Sun and the Earth are always behind you, or the Earth and the Moon are always behind you, depending on where you want to go.
Okay.
And this is many millions of kilometers out. So there's a long communications delay. So, and if you want to control these systems to within these very tight tolerances, you can't be sort of controlling them from Earth. You've basically got to let them control themselves. And the complexity of that control leads us towards autonomous systems. So systems that can look after themselves and maintain those things without a human input.
Okay. And was your PhD done during the Prisma mission or after, or
no?
And you don't care about those kind of formation flying?
Well, yeah. So it's kind of at the same sort of time, but it's different aspects really, because it's very early days. Mm-hmm. There's been many more formation flying missions, but nothing of the scope or the ambition of what is large, very tight formations. It's all building there, and that's where the European Space Agency is funding these missions like Prisoner. That you're getting there, we're getting the tools, and it's basically, you can't go straight into saying, right, here's 10 billion euro, build us a telescope to image another planet, because it wouldn't work. You have to step up the fundamental technologies around the interferometry, around the formation flying. You have to be tested, proved, etc. over a number of years. We're making slow progress. So.
Okay, nice. And what's the main application of this autonomous navigation systems? Like you mentioned, exoplanets. I knew this was about gravitational waves, or also exoplanets.
So the autonomy that I looked at was actually much more general in that I looked at a few missions. So there was a formation flying mission, the autonomy in rovers, Mars rovers, saying that we're looking at the fundamental building blocks here of how you can construct a robust system. Also, I worked on giving Earth observation satellites the ability to autonomously process and choose data. So these are low-level constructs we're working with. And I, in particular, was working with something called multi-agent systems, where you have these very small, self-contained autonomous programs that do their own thing. I thought it was little people doing their own thing. You have teams of them, but it's how you distribute them between different spacecraft, how you have redundancy, and how you can have certain groups of agents on one spacecraft communicating with another group that might be of a different makeup. You have agents going across, it's all.
Okay.
But you build these fundamental constructs, and my work as well was working on ways to define these agent structures. And you can have recursive, an agent made up of lots of small parts. A lot of it's a biological analog in that you can think of the human body as lots of small systems doing their own thing autonomously, like our heart's going, our lungs are going, it's all going. But then as a whole, we are this, I'm this one. We think of ourselves as this one singular system. And in fact, we're made up of lots of subsystems. So it's how to break that down, how to capture that, design that, make it robust, test it, analyze it, things like that.
Okay, so you didn't focus specifically on, for example, the ranging technique?
No. That was just, it was more, that part was, I was looking for applications of these multi-agent systems, and I focused on a few, I looked at a few, but I focused most of my effort on the formation flying, but it wasn't down to the technical parts of the interferometry. It was more, my work assume that's working. We've got this information coming in. How would we manage that sort of formation? Particularly with space telescopes, like distributed ones, it's formation change, formation maintenance. So I did a lot of work on, if one of the telescopes breaks, everyone has to move around, how to do that without crashing, things like that. So things like that, it's great.
Okay. And so did you also work on, for example, adapting the network of data transfers between subsystems?
Yeah, exactly.
In order to make it fail-safe.
Exactly. So you try and have this redundancy built in, and this is where the recursive nature can come in, because you can have the same sort of approach to satellites. If you lose a satellite, what happens? But then on a satellite level, if you lose that subsystem, what happens? And within that subsystem, you lose a part, what happens? And the strategies and structures that you have to be able to verify work beforehand, you can design them in a way that makes it robust, basically. Or knowably robust. You know how it's going to react in a given situation. It might react badly, but at least you know that. Like uncertainty, like with autonomous systems, predictability is a big thing. You have multiple agents doing their thing. It's being able to predict the state, given the randomness of the universe, what's going to happen if something breaks.
Cool. Okay, a bit about outreach, why you do it, and I also want to go on to flat earthers. But let's start with what you hope to get out of it.
Yeah, well, so it's enjoyable. Like fundamentally, it's fun.
Okay.
It's when you spend your days looking at computer screens and equations and code. It's good to get out there. And it's fun. It's really, really satisfying. And a lot of the work in science and engineering research is quite long feedback loops. You can work for a year, a couple of years on something. You maybe have a conference paper, then there's the journal paper, and eventually it gets accepted. You have a few beers, and then on to the next one. There's quite a long feedback loop. Whereas, same with teaching and outreach, you get very, very quick feedback if you're good. or if they're learning anything. That's kind of the same thing. So it's really satisfying. You can go there for 2 hours and you know if you've done a good job or not.
Right.
That's in basically every other part of our job, you don't have that feedback.
And what's the difference between outreach and teaching?
Yeah, so outreach generally, or public engagement, is much more broad. It's getting people, so teaching are people who have enrolled onto the course. They might not want to be there because they're 18 and they're grumpy or whatever, but they've enrolled on the course. Whereas outreach is trying to educate, but in a broader way, give them context so they can make decisions later on. This could be make more informed decisions and understand more of what people are saying on TV or in shows or things like that. Also make decisions on what they want to, school children might want to do with their careers. And we're not trying to say everyone should be a rocket scientist, X, Y, Z, but it's kind of just saying this thing is open to everyone, trying to ensure like equality of opportunity.
Right.
So if someone doesn't want to go into science, it's fine. But you don't want people to think they can't when they might want to. And that's kind of the difference. So we're not trying to make everyone into scientists.
Okay.
Because we've got enough scientists. But it's just to make sure everyone gets a chance if they're into it. And you know that, and you can see it in their face, you see it in the questions they ask of the kids, you see the ones who are into it. And again, I do most of my outreaches around space and space debris in particular, because that's where my career has taken me. But a lot of the conversations they don't want to go into space debris or orbital mechanics. They might want to go into some other thing of science, but just having someone talk to them about a scientific topic goes, oh yeah, I could do that. Or they ask you questions about all sorts of things, like not even remotely related to the topic, but very related to sort of the STEM area.
Okay. Really happy about this answer, because maybe I can elaborate on why. So I saw you participated at the Future for Girls, Engineering the Future for Girls.
Yeah.
And now that you said equality of opportunity, I'm really happy, because I was worried. I have a feeling that at the same time, one pushes for equality of outcome, which is dangerous both for the institution and for people pushed to do something they don't want to do.
Yeah.
And also, I don't want the science to become patronizing in the sense, the scientists. And so I think you nailed both points with that answer.
That's just experience.
But maybe since I was expecting to push back a little bit on Engineer the Future for Girls, maybe you can tell me why you did that, equality of opportunity? Or?
Yeah, no, exactly. I think everyone should have the chance to go into a career in science if they want. I'm a firm believer that scientific ability, or the ability to excel in a STEM area, is evenly distributed to the population. Right? And I'll argue that until the cows come home. Frankly, that's not up for discussion with me, I'm afraid. So with that, a priori statement, it's right. There are some groups who don't think they would be at home or able to undertake a career in science. So you go to target those groups and say, you could if you want. And you don't patronise, you just tell them about normally something cool and say, look, this is the sort of thing people do, and if they're into it, they're into it. And that's it. And it's quite nice. It's those sessions in particular were good in that my outreach used to be more, here's a little lecture about space debris, and then we'll do some like little exercises. But it's evolved over time. And this is for the female only events and also the general events, which we do lots of. Is trying to think about get them. Some people might be hooked on, oh, that's cool, like things in space. But a lot of people are like, all right, okay, and then move on to the next thing. So it's about communicating the impacts of these future technologies on our lives. So we spend a lot of time talking about live video from space, which especially with the teenagers, they're like, what? Because you can show them the video coming from the CubeSats that take a live video of airports and things like that, and cars moving around, and it freaks people out because you say, and believe it, like in 5-10 years' time, that's what Google Maps will be like. There'll be just a layer, the video layer, and you can see basically real time. And we're like, oh, that's cool. But teenagers are like, that is terrible because my mum will always be able to see where I am. And you get into the whole discussion about how you hide from that and things like that. And we also discuss things like the mega constellations, not in a debris sense particularly, but in a, how would it change your life if you had constant internet? And nearly all the students we talk to they're like, well, I've got 3G now, 4G most of the time, it's fine. But you put them in the point of view, okay, but what about everyone else in the world? If there's a blanket internet fast, what does that mean? And it's more the societal impacts, how things have changed. That's how you get them hooked, because like, oh, this is important to me. It's not just cool, because it is cool, but it's like, that's not enough for a lot of people. Because you want to do something because it's worthwhile. Right. You want to see the reason for something. So get them to think about those impacts of things. And I get them to basically say which one they'd rather put money into, which one is better. The video never wins because they don't want to be followed around. But it's interesting to try and get them hooked into what their life will be like in 10, 20 years as these things progress. And these are relatively easy predictions of things. There's also things that we've got no idea will happen, that'll happen, that at the time will be obvious, and we're like, we had no idea that was coming.
Yeah. Okay, nice. So do you think doing outreach, you said that you do it because it's fun, like it's energizing.
Yeah.
Do you think it also helps become a better researcher? Like, is doing outreach one of those moments in which you pull your head up? Yeah,
it absolutely can be. And it's also, research isn't just solving a new problem. Research is also fundamentally communicating that solution or communicating the problem. And if you talk just to your peers in your research group or at conferences, maybe you have it's maybe a surprisingly small echo chamber. You're not pushed to kind of think about things, think about the status quo, think about the larger impacts of things, whereas going to outreach and talking to the school kids, like 10, 11, 12 upwards, like you're talking about these things, and it can't not improve your ability to discuss these things. And it also just makes you think. It just gives you new ways of looking at things, challenges your assumptions, and from a sort of career development point of view, massively improves your communication skills. Because you'll explain something, and you explain it in a way that your colleague who's in, say, an engineering discipline but not yours would understand. And then probably I've no idea. Right. So you try again, and they also don't have no idea. So you've got to think of like 3 or 4 ways of explaining these concepts. And that exercise is really useful because, again, it gives you different angles on how to, and that's where teaching is useful too. Even though I teach a first year class in mechanics, being able to, you can't just understand one way of describing something. You've got to understand fundamentally the concepts and then try and think of different analogies, different ways to look at it. And that's just good mental exercise around communication, which is a fundamental part of research.
Okay. Let's try it out. Are you involved with Stardust?
With Stardust? Yeah, technically. So I'm involved with co-supervising some of the ESRs and working with that. And also, I was very lucky enough to be leading the outreach sessions of the first opening training school, which was good. Right. So for the audience, there's the 15 or so ESRs came to Glasgow, and we did some outreach training. And I'm not sure about your conception of outreach before that. What were you expecting from that course? What did you think it would be like?
I had no idea. Like genuine. It was nice to discover a lot of tools. For example, the thing we used to during the class. Let's say you put on the screen a code and we give a feedback. And we discuss the feedback real time. I've never seen that.
That's how we teach. That's how I teach the first year. So.
That's interesting. But yeah, I mean, you gave me the chance to develop this idea.
Well, yeah, that's it. So it's
like an open field to discuss. To do something.
It's like when I was asked to do it, some people are expecting, okay, you have make some worksheets and think of an activity for people to do. But we took a kind of a step back and just thought about what outreach is, what we want to do, how, and we came to the conclusion that it's talking to people. And so what's the best way of engaging with members of the public? Because we all went to the Science Centre on the Saturday, Glasgow Science Centre, and we had to get out of our comfort zone and start talking to people, and you all did excellently. It's always a slow start. They wanted to you have to lose the ego. You have to lose the ego in teaching and in outreach too. You can't, because you're not always right in these things, and it's hard and you'll fail. But you have a go, and we talked to members of the public, and we had many protests and things like that going on, which is all fun. And I think it worked really well. It was really, really nice. But it's, again, stripping it back to the sort of the fundamentals of, it's not about making a nice worksheet or a fancy video. It's about how do I communicate with people. And if I'm training someone to do outreach, the vast majority of the time should be spent with them talking to people, because that's how you learn. because as you were talking to members of the public, the questions are never what you expect. What they understand in some areas was way more than you expect and way less in others, and it's adapting to that and trying to remember you're just trying to engage them. You're not necessarily you're going to test them. So you want to get them more informed, more engaged, and able to take the next steps if they want.
Right. Okay. To wrap it up, let's go with a Stardust explanation for 3 years old, then 10 years old.
Okay.
20, and then...
So what is Stardust?
Let's say something interesting that a 3-year-old can understand, and then up till about the space debris.
Yeah, okay. 3-year-old's tough. I would, for a 3-year-old, they will have, probably a conception of space and stars and the moon and things like that. So I would say we are working to make sure we can continue to go into space for their lifetime. That's probably my 3-year-old one. I'm not sure they even know what an asteroid was.
Yeah, it's tough for a 3-year-old.
Yeah. And what's the next one? 10.
10.
10. Well, the thing is, as soon as you get to 10, you don't have to tone it down.
Right.
You say what it is. We're working to research the dynamics of how asteroids move, how space debris moves long term, building tools and techniques to make sure we can understand what they're doing. So asteroids don't hit us, and we can still have access to space through space debris. For 10 years old, you're already there.
Okay.
And then
where's the tipping point?
Oh, that's it. It's lower than people think. Like 10-year-olds, I talk to 10-year-olds, they absolutely get what we're doing. Like not in a technical aspect, but then adults, like, or if you're not in a technical field, you're not going to get a technical aspect. So you can understand the reasoning and the description of the thing. I think as soon as they have the vocabulary to understand what an asteroid is, what space debris might be, satellites and breaking up and things, you can explain that. Okay, these are the things we want to understand what they do, how they move.
Mm-hmm.
That's
okay. And something for an aerospace engineering lesson?
So we're developing across the board some very, very cool tools and techniques about modelling the complex dynamics of other bodies in the solar system. I think it's a very exciting time. We have the tools to describe the motion of a body when we know what it's made up of and where it is have been there for hundreds of years. We can predict orbits very well. Halley's Comet, it can be done. What we're getting to now is that how can we predict these motions, see what they do, the behaviour of these objects, be they asteroids or space debris, when there's uncertainty there, when we don't know their shape, we can't see them directly, we can't know much about them. With that said, how do we actually tackle removing debris? Or more importantly, from my point of view, it's not the removal of debris is the problem. We're still a step before that. It's understanding how the debris behaves. And that might seem giving it some agency of its own. It don't do its own thing. But it's, as a population, we are very uncertain about large aspects of that population. Like sizes, shapes, motions. We know generally, but we don't have much information. So it's finding what's that long-term behaviour. Given what we're doing now, how will that behaviour change? How will the population change? And then from that, do we want to remove those objects? And if so, which ones? Right. And for the asteroids, it's more similar to some of my previous work in that you can see you've got the target asteroid, but you can't, once you get there, you want to be in orbit around the asteroid. And they're not big objects, it's a very tenuous orbit, let's say. A lot of uncertainty. So it's got to be able, these systems, we've got design processes and systems to be able to autonomously navigate, do their own thing out there because they're quite far away. We can't directly control them. And to be able to explore these outer bodies and find out much more because we're still at the very, very early days of landing things on asteroids and comets.
Right. Exciting.
It's very exciting. It's very cool. Yeah, and also, so another thing as well, it's a good time to be doing this because there's a whole suite of tools and techniques. So traditionally we do a lot of maths, and then it moved towards more stats, statistics, lots of numbers. But now all the tools coming from the machine learning, the big data side, which is an extension of stats and maths, like it's not some separate thing. But those tools have become much more powerful. They're computational tools, so we can really tackle some problems we couldn't really tackle robustly perform. So I think that's very exciting too. And a lot of the Stardust researchers have some different aspects of machine learning and big data sort of aspects in their work, which I think is cool.
Let's see how it turns out.
Oh yeah, well that's it. Proof's in the pudding.
Yeah. Okay. Thank you for your time.
No, thank you, Matteo. It was great. Thank you.